Sure. Yeah, thank you. I hope everybody's had a great conference so far, and I hope I can live up to the great presentations that we had earlier this week. Before I get started, I should just say that a lot more people contributed to this work than I did, and their information will be somewhere near the end of the presentation, along with the details of the paper that we published together recently. But yeah, first, my name is Nathan Beech. I'm a PhD student at AVI, as was just said, and today I'll be presenting on the impacts of climate change on ocean eddy activity using CMIP6 simulations from AVI-CM. I won't spend too much time on the sort of introduction thing, since I think you've heard it all before this week, and you were probably pretty familiar with it before that. Very briefly, though, on the left here, your left, yeah. You can see eddies simulated on the phasum grid, and maybe it's not going so smoothly up there, but on my screen, it looks great. Yeah, these are rings, and on the right, wherever we have a lot of eddy activity that we see on the left, we get a lot of eddy kinetic energy. So on the right, this is eddy kinetic energy as observed from satellite altimetry. And that is the quantifier or the indicator of eddy activity that I'm going to be using in this presentation. Again, I won't spend too much time convincing you why we care about eddies, because probably this crowd already knows very quickly. Ocean circulation, we know that eddies don't just appear where the mean flow of the ocean dictates that they should, but actually, for example, we can't effectively simulate Gulf Stream separation without eddies resolved. So eddies themselves can have an impact on ocean circulation. Eddies also bring with them the conditions of the ocean where they were born to where they end up. So for the physicists in the room, that means heat and energy transport. And for the biologists, if there are any here, that can mean nutrient transport as well. Eddies can facilitate gas exchange, which brings them into the important topic of climate change through carbon sequestration. But perhaps a more interesting topic for this group here is that for a long time, we couldn't really look into mesoscale activity with climate models effectively because of the computational demands of simulating the mesoscale. So one reason for us to look at this may be because we're interested in what is unexplored. And with that in mind, let's remind ourselves what the resolution requirements for simulating eddies are. I know you've already seen this this week today as well, so I'll be quick. The rule of thumb to simulate eddies is that you need a grid resolution of 1/2 of the local Rossby radius, or 1/2 of the radius of a typical eddy, wherever you are. And that varies generally with latitude. And to put that in the context of climate modeling, the highest nominal ocean resolutions in CMIP6 were 25 kilometers. Now, I know that a nominal ocean resolution doesn't necessarily mean that that's consistent everywhere, but we can use it as a jumping off point to see what a 25 kilometer grid resolution gets us in terms of the local Rossby radius. And what you can see here is that outside of the tropics, we can't expect a grid like this to simulate eddies. So in CMIP6, AVI-CM also had a nominal grid resolution of 25 kilometers, but of course what makes AVI-CM unique, and more specifically what makes PHASOM, the ocean component, unique, is that it uses a unstructured mesh to smoothly vary ocean resolution in space. And it does that using spherical triangles, which I've zoomed in on here, as opposed to traditional rectangular grids. The grid, or the mesh that you see on the left here, is the one that was used in the CMIP6 deck experiments by AVI-CM. It has about 830,000 ocean surface nodes, which puts it roughly on par with a traditional quarter-degree model in terms of computational cost. And then to look at that in terms of the local Rossby radius, we can see that with this distribution of resources, we can approach or exceed the 1/2 R threshold in all of the western boundary currents. And as well, we approach it in the ACC as well. So then how did AVCM perform? On the left here, you're seeing eddy kinetic energy as simulated by AVCM during the observational period for which we have satellite altimetry data. And on the right, you're seeing eddy kinetic energy as observed by satellite altimetry. And so you can see that AVCM performs quite well. The magnitude and spatial distribution of eddy kinetic energy pretty well matches the eddy-rich regions of the global ocean, particularly in the western boundary currents and to some extent in the ACC. And you can also see that there are some common weaknesses here. For example, Gulf Stream separation seems to follow the typical biases that we find in lower resolution climate models. I can tell you while we're looking at this that the model data set represents between 50% of observed eddy kinetic energy in the ACC, just over 50%, to just over 82% of observed eddy kinetic energy in the Kuroshio. And so that allows us to make some of the first long-term projections of eddy kinetic energy, ocean eddy activity in climate change with a ensemble of simulations at the scale of a CMIP dataset. And so that's exactly what you're seeing here. This is the difference between eddy kinetic energy at the end of the 21st century under emission scenario SSP 370 and at the beginning of the historic period. I can tell you that eddy kinetic energy in this plot is calculated using ocean velocity anomalies that are first calculated from sea surface height to put it on par with the observational data set, but as well the velocity anomalies are calculated relative to a running mean. And that allows us to account for changes in the mean state of ocean flow while we calculate our anomalies and while we calculate eddy kinetic energy. And so a few things are probably going to stick out right away, and perhaps the most striking is the poleward shift of eddy kinetic energy in most of the western boundary currents. So we have this dipolar pattern where eddy kinetic energy increases towards the poles and decreases towards the equator, and that seems to reflect a spatial shift of the eddy-rich regions that correspond to these western boundary currents. And that's something that's been observed and projected in the context of climate change already, primarily due to winds. And you'll probably also notice that the Kuroshio stands out as an exception here. And we'll get into each region a little bit more specifically right now. So let's begin with the Gulf Stream. Here we can see our spatial shift in the map on the right. And also on the left, I have the time series of eddy kinetic energy with ensemble members in gray, the ensemble mean in black, and observations in red. And so clearly towards the end of the 21st century, beginning in the mid-21st century, we have a decrease in eddy activity. And what this plot probably brings to mind is the widely anticipated decline of AMOC. This is something that's been speculated on a great deal. And so the connection here could be that as we get less AMOC through the North Atlantic, we get less energy transported through the Gulf Stream, which means less energy available for conversion into eddy kinetic energy. Whoops. To put that in the context of the observational record, so in red here, there is an increase in eddy activity observable, but this change is statistically insignificant. And then in the model ensemble, so the ensemble spread is shaded here, and the ensemble mean trend is the dashed blue line. And so we see the ensemble mean is pretty close to zero. The ensemble spread includes both positive and negative trends. And so, although it doesn't really look like it at first glance, the data sets are in somewhat of agreement in that they are both inconclusive during this period. And so what's interesting is that the long-term decline that we see may begin soon as the observational record grows. Moving on to the Brazil and Malvinas currents, here we have a substantial increase in eddy activity. And the reason for this could be the same as in the Gulf Stream, in that AMOC decline may be responsible. So the theory here is that as overturning circulation through the Gulf Stream declines, the heat and salinity that builds up in the tropical Atlantic may increasingly take a southward route to escape to the higher latitudes. There's evidence of this in paleoclimatic records during transitions from glacial to interglacial periods, where we see an increase in transport through the Brazil current. And so digging into the model data set a little bit more, we looked at changes in volume transport in the North Brazil current and the Brazil current, and we found that volume transport through the North Brazil current declines as eddy activity in the Gulf Stream declines, and as well volume transport through the Brazil current increases. So there's the change. And so that lines up pretty well with the changes in eddy activity that we see. Both the modeled and observed data sets show an increase in eddy activity during the altimetry era, but we project that to increase in the context of climate change. So the Kuroshio current is probably the most perplexing of the regions that I'll talk about today. We already saw that it doesn't follow the same poleward shift that the rest of the western boundary currents seem to. And there's a few theories for that, which I won't get into too deeply. But there's also another feature here that I want to point out, and I think this came up a little bit already this week. So in our time series here, we'll see some spikes in the eddy kinetic energy of individual ensemble members at various periods. And what I can tell you is that this circular feature here is what's responsible for that. And you may be able to tell that this circular feature of rising eddy kinetic energy corresponds to the paths of the large meander and non-large meander of the Kuroshio. So essentially, the Kuroshio is a bimodal current. It can take one of two paths. And that makes it difficult to characterize the mean flow of the ocean here, and then difficult to characterize velocity anomalies. And so whenever we have a transition from the large meander to non-large meander path, that is interpreted as a spike in eddy activity. And so I think this conversation came up a little bit earlier in this week in how we define eddy kinetic energy in terms of temporal variability or spatial variability. And so it is a trade-off in terms of how we define this. One way that people do get around it is using a shorter running mean, something like 90 days, because the transition between the large meander and non-large meander paths can occur on timescales up to 1 decade, which is a much lower frequency than we typically associate with mesoscale variability. So we just need to keep this in mind when we interpret these results. Despite those challenges, we also see an increase in eddy activity in the Kuroshio current. And one reason for this could be that Kuroshio current volume transport is projected to increase. This is mainly due to increased stratification as well as increased wind stress over the recirculation gyre. So that's one theory for this. But as I said, this is probably the most perplexing region that I'm going to go over today. So if you have thoughts on it, I would be interested in hearing them. And finally, both the modeled and observed data sets show an increase during the altimetry era, but we again project that to accelerate in the future. So in the Agulhas current, we don't see a substantial change in the magnitude of eddy activity, but there's still a lot that we can tell here from changes in the eddy field. So if you follow this red circle, you'll probably notice that we see an increase in eddy activity where we typically find Agulhas leakage occurring in the form of Agulhas rings. So transport of warm, salty Indian Ocean water into the South Atlantic typically takes the form of mesoscale eddy activity. But that being said, that's not necessarily a good indicator or quantification of Agulhas leakage. And so looking into the rest of the model data set, we can also find this is supported by volume transport changes. This is something that's already been projected in the context of climate change, and for a few dynamic reasons, which we'll get into later. So, as well, looking at the spatial changes of eddy kinetic energy, you can also notice a southwestward shift of what appears to reflect the Agulhas retroflexion. This is something that's also associated with greater Agulhas leakage, as well as lower overall volume transport through the Agulhas current. And so to tie all of these things together, the mechanism behind it seems to be that there is a southward shift of southern hemisphere westerlies. This is something that's already been observed and is projected to continue. And this results in a southward shift of the boundary between the subtropical gyre and the ACC. It also results in lower wind stress curl over the upstream Agulhas and decreases volume transport. That in turn allows the Agulhas to continue further up the African coast before it separates, meaning it separates further towards the Atlantic and with a more zonal path. And this allows greater Agulhas leakage. At least that's my understanding here. And so we can really tie all of these changes together, just starting by looking at the changes in eddy activity and then following where the rest of the model data set and the published literature leads us. Another interesting feature here is that both the modeled and observed data sets seem to agree that there is an increase in eddy activity during the altimetry era, but we do not project that to continue. The last region that I'll go over today is the ACC. Here we have another substantial increase in eddy activity. And the reason for that is expected to be the intensification of southern hemisphere westerlies. But in this region, the relationship may not be as simple as increased wind stress, increasing energy, mean flow in the ACC, because the theory of eddy saturation tells us that after a certain point, increased wind stress will no longer increase the mean flow of the ACC, but instead just result in increased eddy activity. And so to investigate that, we looked at volume transport through the Drake Passage, which is not a perfect representation of ACC strength, but is the choke point of the ACC.
Very low. Connected to.
And so what we find here is that the change is not substantial. I can tell you that the difference between the early historic period and the end of the projected period here results in a difference of about 2%, which is probably physically inconsequential, and as well, we would expect the other trend if we were expecting an increase in ACC strength. And so what that suggests is that the ACC simulated by PHASOM is at or around its eddy saturated state. Now, interestingly, the ACC is the only region in which the observable change in the model dataset is consistent with the long-term projected change. And so we can expect that the observable changes here will continue. And I want to make a final point about how we characterize changes in eddy activity. So throughout the presentation, I've been showing you linear trends in time of ACC. And in that case, linear trends in time in EKE. And in that case, the ACC is the only region where we find consistency between the observable and projected period. But actually, I wanted to avoid linear trends altogether in doing this work and writing this paper, because we know that, for example, climate change does not necessarily occur linearly. Temperature rise does not necessarily occur linearly, and the same goes for carbon emissions. And yet there was still a demand for us to quantify the changes in eddy activity. And so what we ended up doing is this on the right here, where we express change in eddy activity in terms of temperature rise. And I think this works a lot better in the sense that you have sort of a clump of points where during the historic period we don't see much change, and after a threshold of 1 degree temperature rise we get a nicer relationship. And as well, I hope that this makes the conclusions that we find here more applicable, considering that this is an emission scenario that might not come to pass. And so hopefully this relationship is useful either way. So to conclude, I think what's really remarkable here is that AVICM was able to reproduce mesoscale eddy activity in the context of CMIP6. So these are really intense simulations, and by distributing computational resources efficiently, we were able to simulate that activity. And then we project substantial changes in eddy activity in the various regions. And we don't just have to rely on the model being the truth to reinforce those changes. We're also able to connect the changes in eddy activity to the rest of the model data set, as well as the published literature and what we expect to change in the context of climate change. And finally, in most regions, the observable changes do not seem to be reflective of the long-term projections, either in character, so in increase or decrease, or in magnitude, so whether or not they will accelerate. And here is the paper that you can look up if you're interested in reading more. And thank you.
Thanks a lot, Nathan. Very interesting indeed. Oh, nice movie. Questions? Saren.
Yeah, thanks for this very interesting talk. I have actually quite a few comments and questions, but I would like to start with a very general one. So if you go to your conclusions, the first one was that your model nicely represents the observed pattern of eddy kinetic energy. And I generally agree, but I also realized that there are two areas which are actually, I think, not very represented, that I would think they're key. So on the one hand, you really don't capture the high eddy kinetic energy and the area of the North Brazil current rings, which constitute a very important pathway of the upper AMOC, and also you don't capture the elevated EKE in the Mozambique channel, which is also really important for triggering and setting EKE in the Agulhas region. So what I was wondering is, did you not refine the grid in that area, or were there other reasons that you didn't manage to capture these EKE patterns that I would think are crucial?
I think the most simplistic answer is that this mesh is already quite tight. So of course we would like to resolve everything, but it's CMIP6 and it's a very intensive simulation. And so absolutely not everything is well resolved.
Is the grid in theory fine enough in that areas to reproduce the eddies, or are these other boundary conditions or so that are needed there? That was more the question.
Sure. So there you can see the grid, and there you can see it in terms of the Rossby radius as well. And I guess this is a difficult question because, in theory, what is necessary to resolve eddies, that's not so clear. The rule of thumb is 1/2 of the Rossby radius, which I guess in the Mozambique channel, for example, we do get that. Another thing, though, that we've learned in designing these meshes is that just putting the resolution where you want to see eddy activity isn't enough. You need upstream resolution to create perturbations that can sort of seed eddies. And so there's a lot to consider. So I don't really have a satisfying answer as to why the weaknesses in resolving eddy activity that we do see with this mesh are there, but there's a lot of reasons that go into it.
Just a connected question from me. Why did you offer a quarter of throughout the whole equator? There might be a good reason, but you could have taken those points at the equator to fill in others.
Yes, that's a good point. I think the reason is that mesoscale activity is not the only thing that we're interested in. And as well, it's not difficult to reach 1/2 of the Rossby radius around the equator. So it's not so much that resolution was piled up there, but just that it has a bigger impact there.
Thanks, Nathan, for this really, really awesome talk. I might have missed it, but did you say anything about how the mean kinetic energy changes in any of these places? And do you know if there is a bit of a is there any sort of repartitioning between the mean and the eddy reservoirs that's going on?
So to begin, I didn't really show changes in mean flow other than changes in volume transport, so changes in the magnitude of mean flow. And so yes, there are changes, and they do have an impact. So if you don't account for them when you calculate your velocity anomalies, then that can appear as a larger anomaly in magnitude, and then you can overestimate eddy kinetic energy. And the same actually goes for spatial changes in the mean flow. So, for example, everywhere you see a decrease in eddy activity here, you, especially along the western boundary currents, you tend to also see a decrease in mean flow, not necessarily that the magnitude has decreased, but that it's moved somewhere else. But when you're looking at that in terms of one grid box, it can appear as a decrease, and then that can be skewed. That can skew your eddy kinetic energy, and so that's why we use the running mean to account for that.
Hi Nathan. Yeah, thanks for a really nice talk. You sort of touched on this, so it's kind of really sort of just me trying to clarify things. So there's this question about how you define EKE, whether you use like the time mean or the spatial mean. I think you're using a temporal definition, right? That's right.
Yes. So we use time. I can explain the whole thing. So first we split the year into 5-day means. We remove leap years so that it's divisible. And then for each 5-day period, so say January 1st to January 5th, we take the mean of that 5-day period for 21 years. And we also take the ensemble mean. So this also came up, I think, in Takaya's talk earlier, that there are pros and cons to doing that. But we did that to increase the sample size from which we can calculate the mean state so that we get a clearer mean state. And as well, since we do have a changing climate, so the other opportunity to get a larger sample size to calculate your mean state would be to increase your running mean window. But to go from 21 years, so 21 data points, to 5 times that, which we get from taking the ensemble mean, that would be a lot of years. And so you would lose all of the change that you get from climate change. And so that was our justification. But it is, there are pros and cons to it. And so, yeah.
Yeah, I suppose, sorry, just to follow up on that. So one of the things we know at a quarter degree model, you tend to get standing eddies, right? So I suppose, you know, a spatial filtering would show up those standing eddies a bit more than a sort of temporary filtering, but yeah.
Yeah, absolutely. And I think especially the point that I made about the Kuroshio is that you really have to keep in mind what you want to identify and then make sacrifices in order to do that. So rather than account for standing eddies here, we took another approach. But it's a fair point, and I think these are sacrifices that you have to make no matter which method you go with.
Mike?
Yeah, it's a very nice talk, Nathan. Thank you for that. I'm wondering whether you've looked at the deep western boundary current in the North Atlantic. So particularly if you have a northward displacement of the Gulf Stream like that, which I think is what your eddy kinetic energy is reflecting. I think if you have a very decreased deep western boundary current, that would help to allow the Gulf Stream to displace like that. So under these sorts of climate change, you might expect the deep western boundary current to decrease quite a bit. And it'd be interesting to see that. And of course, that wouldn't happen in the Kuroshio region.
Okay, yeah, very interesting. So that could then explain the sort of contradiction between the two. Yeah, fair enough. And sorry, to answer the question, no, we didn't really look into that.
Yeah, really beautiful talk and beautiful model. One of the things I noticed is that your ACC is very consistently around 171 Sverdrups. This makes me jealous because it's so spot on with the observations. And my question is really, did that just pop out? Did that emerge? Or when developing the model, did you turn some knobs to get it so incredibly spot on?
I can't really answer that well because I wasn't even at Avi when these simulations were run and when this version of the model was developed. This is Phazon 1.4. So I can't really answer that spot on, but I do know that when they were evaluating the model, they weren't just using they had a few different observational estimates of ACC transport, which weren't all consistent. So I don't think that they would have chosen one and gone with that.
I mean, this is the Donoghue et al., which is the most recent and the most thorough assessment.
Yes.
So therefore, a lot of people would give that priority. But
right.
Yeah. Okay. Thanks.
I'm just curious about changes, say, in the Arctic. You don't see much of a signal there. Is that related to how the ice is changing in the model simulation? Not because I would definitely have expected, as the ice retreats, more enhancement. And I know I've seen some of the other Phazon stuff that really has some very significant eddy kinetic energy, West Spitsbergen current going in around Svalbard and that. So is that function of... Again, I guess that needs the much higher resolution because of the Rossby radius. Like, did you look at, say, the changes in the ice field, so at least you might have an idea of where you might get eddy changes if you could resolve them at those higher latitudes?
So the reason that they aren't there is absolutely the resolution. So we didn't really look into that. We did look at changes in eddy kinetic energy there. We saw an increase, but it's probably not robust. It's absolutely not robust. And so I didn't really look into changes in the ice field in this simulation, but people are doing that with higher resolution simulations at Avi right now. Yeah. So.
Well, thank you for a very nice talk. Very much enjoyed that one. Quick questions regarding the strengths of your northern western boundary current. First, the Kuroshio, I think that's the only... I don't think you show the strength of the Gulf Stream, but you show the strength of the Kuroshio. And I seem to remember it was 10 Svidras, but it was average of the top 100 meters. So how strong is it actually? Because I mean, it reaches deeper than 100 meters. So what's its total transport roughly?
So I did calculate that at first, but then, as you probably all know, characterizing a current isn't a trivial thing, and so choosing which depths to look at for each current was a very involved process. The reason that we used 0 to 100 meters for the Kuroshio is for a couple of reasons. One, there's some evidence that there's a disconnect, or there has been a disconnect between the surface layer Kuroshio and the deeper Kuroshio in terms of a spatial shift. And as well, the papers that I cite here are not looking so much at the deeper ocean in this region, and so that's why we chose the first 100 meters. And I don't remember off the top of my head what the strength was.
Okay. And for the North Atlantic, I mean, you related with the decline of the AMOC. So, but are you confident that the Gulf Stream itself has actually decreased? I mean, and it is consistent. Your changes of EKE are consistent with a shift, with a weakening of the Gulf Stream. But have you actually looked at that? Has it actually really weakened? Because a weakening of the AMOC, in principle, doesn't have to coincide with a weakening, because you can think of circular. It may just be a change in the preferred pathway, surface pathway versus deep pathway, and you may have an AMOC that declines, but a Gulf Stream that remains unchanged. I don't think this is what you have, but just wonder if you checked.
No, I didn't check.
That was a short answer.
Yeah.
Yeah, I was waiting for a bit more specific comment. Thanks again for this great also discussion. I learned a lot. Can you go to the Agulhas region? And I worked on that region a lot. So we published a new paper. I was just wanted to say that I find it really interesting that you also said that the eddy kinetic energy and the strength of the Agulhas leakage does not always go one-to-one. That's also, I want to make a little bit advertisement for our latest paper published in December, where the group of Arne and also Franziska Schwarzkopf, we really try to summarize what we find there, and that's actually in agreement also what we find, that it's not always related. And I wanted also to ask you whether you have a feeling about the general strengths of your leakage, because it appears a bit high, and that it looks also from your pathways as if the transport might be a bit too laminar and too strong. Just a cautionary note there.
Yeah, I think you're absolutely right. And first thing that I'll say is that a lot of the connection to the literature for this region comes from Arne and that group at Geomar. So yeah, absolutely. This quantification of Agulhas leakage on the bottom is also not a perfect assessment. It's volume transport over a transect that we chose. And the reason for that is, you know, there are a lot of creative ways of quantifying the transport, like with drifters passing a threshold, and then you assign a volume to each of them. But obviously this simulation wasn't run with that in mind, so we did what we could, and I think the consistency here between the model data set, between the data set and the literature is good enough that we can be pretty confident. But you are totally right that that it's not a perfect quantification.
I got a question. There is something I always hesitate to publish about our simulations: trends.
Mm-hmm.
How confident are you in the externally forced origin of such trends? Could that be the model getting towards its own climate, if you wish, or final state?
So I will just say that obviously model drift is a big problem, but these are CMIP simulations, so they have one of the longest spin-ups of model simulations that you'll find. So I don't think that this is model drift or anything. We can compare to the pre-industrial control run, and I don't think you see the same thing. But I guess that's all I can say, is that probably not, but I can never be certain.
Could it at could that be useful to look at the differences between the trends in the two classes of simulations?
Absolutely, yeah, and that's one thing that we considered. But frankly, I think the signals here are strong enough, and when they occur, suggest that it's not model drift. These didn't occur at the beginning of the pre-industrial control, and it would be strange for it to take 500 years plus to start.
Other questions? TK. Yeah, ensemble mean. Ensemble mean.
Well, yeah, I guess Thierry just said ensemble mean, but you already kind of explained that you did use an ensemble mean, so my question's a bit different. And this might be kind of an unfair question, considering that, let's say, coarse ocean models always get the North Atlantic current passway wrong, or I mean the Gulf Stream separated Gulf Stream tends to be too zonal. And I was remembering how the mesh spacings were spaced, and it seems that you raised the resolution around the Gulf Stream, but not necessarily northward of the separated Gulf Stream. And I was wondering, because of that, like okay, maybe you did northward as well. But yeah, I guess I was wondering, because towards the north, the resolution tends to be, at least compared to the Rossi radius, coarser. That sort of how the Gulf Stream goes out is sort of like locked in by the regions northward, where like everything has to be connected through, let's say, volume conservation and or mass transport conservation. I'm not sure if my question was clear.
Yeah, I mean, so what exactly is the question?
So it's I just was wondering whether, even though you have high resolution in the Gulf Stream region, because outside of it the resolution is coarser, that the Gulf Stream is sort of forced to flow out towards, in order to match how the flow is in the coarser resolution area.
What I can say is that we have done simulations with higher resolutions, and we find that improves the path of the Gulf Stream, but it's not enough to make it perfect. So I think there's no easy answer in getting your Gulf Stream separation right. And it's true. I would agree that, yeah, just increasing the resolution where you expect eddies to occur, or where you expect this flow to be, is not enough.
Okay. We have a question online, and I see that then Mike has a final comment maybe, and we should probably close the discussion then. So Jérôme, would you be able to formulate your question online?
You can't see it. Well, it's a question about the coupling, the wind current coupling in your model. So I guess that your atmospheric model is pretty coarse, coarser than your higher phasor mesh. And also, I would like to know if you do use relative or absolute winds.
Yeah, so you're totally right that the difference between resolutions in the atmospheric grid and the ocean grid is a problem, and it's known to have an impact on eddy activity and on the model itself. And as well, I believe absolute winds were used here, and that is as well known to have an impact.
Mike?
Yeah, just following up on a previous question. I mean, it looks as though you've chosen your grid spacing to try to get the northwest corner. And I noticed that the eddy kinetic energy didn't match up, perfectly. I'm just wondering how whether you get biases, in the coarsest resolution models, you get a big cold spot in that region, and do you manage to avoid that in your simulation?
I don't think that it's entirely avoided, but to be honest, yeah, I don't have that information off the top of my head. It might be in my citations here. There's another paper that did the sort of evaluation of the CMIP6 data set as a whole. So I would just have to refer you to that paper.
Well, thank you very much, Nathan, again. Great talk, and thanks to the audience.